Hello everyone and welcome to Moving Mountains, how infrastructure as code unlocks massive refactoring possibilities. My name is Sean Virch. I am an engineer at OSO, an authorization service provider, and today we'll talk through how Pulumi helped with a major migration of the OSO infrastructure. Infrastructure refactoring is something that I've spent a lot of time thinking about. Over the last 10 years, I've worked at a number of different startups at completely different stages of infrastructure maturity, and I also spent a lot of time on a government modernization response team. So in that group, we were responding to projects that had some urgent infrastructure issue that needed to be resolved. So sometimes we had to do an infrastructure refactor extremely quickly while still making sure we were doing it safely. And my takeaway from all of those experiences is that the number one most important factor is what tools you have access to. So there was one project I remember working on that had started in the 90s, and they had very little tooling available. Even their pitch deck said things like, you should use us because we use the internet and we're Y2K compliant, which at the time the project started made sense, but they gave us a sense of what we were dealing with. Even the development setup required a sysadmin team to go set up a bunch of custom libraries, a bunch of custom tools, and when we complained about this, they created a disk image to include all the custom libraries and tools, which didn't actually solve the underlying problem. On top of that, they had a custom development test environment, and this environment was shared by everyone and had no tracking of what changes were made. So debugging consisted of everyone standing around speculating what might have broken with no true ability to actually understand what change caused the issue. So a lot of this was very human, very manual, and we really did not have the ability to get a lot of things done here. The very next project I worked on used AWS and Terraform. Now, this project still had some infrastructure challenges and some things that needed to be fixed, but the fact that we had access to modern tools meant that the scope of what we could safely change was an order of magnitude beyond what we could have done otherwise. And so this is how I started thinking about infrastructure refactoring as a concept, because I saw that wild difference between what we could change when we actually had the right tools and what we could change when we didn't. And so I want to talk about Pulumi and OSO here, but I just wanted to talk about why I'm interested in this personally and why I want to think about how we can use the tools we have more effectively. So let's talk about OSO's architecture. OSO is an authorization service provider, meaning we can respond to queries about whether a specific actor should have access to a specific resource. Does Alice have access to this folder? Does Bob have access to this document? Is John in this group? This is difficult to cache because the questions might be different every time. But at the same time, it also has to be extremely low latency and high availability because authorization is in the critical path of requests. Our users can't respond in their applications until they actually know that their users are authorized to view a specific resource. In order to deal with this, we replicate our entire dataset onto every service instance. Now, this is not necessarily what you would do in every situation, but because latency is our number one priority, we had to do this. So this does make reads very fast and scalable because each service can respond using its local copy of the data. To make this work, we have to replicate writes through Kafka, and whenever we need to spin up a new service, we restore a recent snapshot from S3. So this architecture has some nice properties. Reads are fast, satisfying our main design goal. The source of truth is S3 and Kafka, meaning that we could rebuild the entire company even if we lost all of our services with only an S3 snapshot and access to our Kafka queue. And the fact that each service has its own dedicated storage makes it easy to reason about concurrency and the application design. And finally, the fact that we're deployed on ECS Fargate means that AWS does a lot of the management for us, including rolling updates, scheduling containers, and auto-scaling. So our architecture overall is simple in the end from our perspective. But this can't last forever. The storage size of authorization data is small. We're not storing images and videos, we're only storing metadata relevant to authorization, which doesn't take up that much space. So this is what let us get away with this simple architecture. But we reached a point where the initial sync started to become too slow because our company started growing, we started getting more users, more data, and slow deployments mean a slow development cycle and a long incident recovery time. On top of that, it meant that the snapshot service became critical path because a stale snapshot means that new services have to process more messages in Kafka to get up to date after they've done their initial sync. So this was one badly timed combination of issues away from a major incident that we couldn't gracefully recover from. So we needed to change something. But there are some challenges here. Because we need our service to be low latency, it's deployed in 12 different regions so that applications can be routed to a service that is geographically close. There were also thousands of lines of existing code that reflected what had been learned in years of development on this project. On top of that, the application itself and everything around it was built around the assumption of dedicated per-task access to SQLite databases on dedicated volumes. And even though it's not the source of truth, we still have to think about state because these are persistent, at least for the lifetime of the task, or however long we decide to keep it around. And finally, we need to make sure this isn't a major performance regression because that is our main design constraint as an authorization provider. So just to give one example, when we know we're the only service who will access a SQLite database, we can tune our SQLite clients and turn off some of the more expensive durability settings because we don't care as much about persistence. So these are some of the things that we had to consider when thinking about how to update this infrastructure. On top of that, we had other work to do and didn't want to sink our time into changing absolutely everything. The solution we came up with to meet those challenges was to try to keep ECS, but to take over the management of the hosts that the tasks are scheduled on. This meant that we could still take advantage of the things that ECS helps with, avoid changing our whole deployment pipeline and application design, but still get more control over the storage layer. So instead of each task having a local copy of the data, each host would have a local copy and the tasks on that host would share access. This would allow us to decouple the deployment of our service, which is running ECS tasks, from the lifecycle of the underlying data. If we did want to resync, we could do that by recycling the underlying hosts. But if we don't need to resync, we can just redeploy the ECS service and redeploy the tasks on the existing data without having to do a resync. Of course, this is a very idealized story, and we still had to change quite a bit about our application. I'm not going to talk too much about those details because those are really unavoidable. If your system allows for something, if your system allows developers to do something, someone will write code to take advantage of it. I even heard a story about a project that relied on SQL injection to function properly. So if anyone wanted to remove the SQL injection, they had to rewrite part of the application so that it no longer used SQL injection to work. So really, you cannot take anything for granted. So of course, the next question we need to ask ourselves is, how can we avoid breaking everything? This was my first major project at OSO, and this was a major change in how the service is deployed. It's breaking all the assumptions that I talked about, all these unknown assumptions that have been built up over the years, and our Pulumi code was all in one monolithic stack. So that's really the point of this talk. This migration strategy at the infrastructure level allowed us, and more specifically allowed me, as someone without experience in the infrastructure, to safely untangle all these pain points without breaking anything for existing users. So the advice that I want to share today roughly fits into 3 categories, and they also happen to chronologically match the way the refactor played out. So first, there's something that I just started calling a zero-diff refactor, which is not conceptually that complicated, but was really the only reason that this was possible. Next, I want to talk about some of the patterns that we had to untangle, some of the things that were painful about the migration that we were able to do because of the zero-diff refactor. And I'll also talk about how the Pulumi programming model is a bit different from other software. And finally, we'll get to the payoff. I'll talk a bit about the migration itself and how we ended up with our new infrastructure and what the result was. So what is a zero-diff refactor? The concept itself is not that complicated, but this is what made the migration possible. The idea is that you want to make changes that result in no diff when you run Pulumi preview. This allowed us to make massive changes, resulting in some completely unreviewable PRs. But Because we knew that this change wasn't changing any real infrastructure, we could be confident that this wasn't breaking anything. We didn't even need to run PulumiUP after merging this because there was zero-diff. So this is important because I didn't know which parts of the system were important to keep around. I didn't know which parts of the system I shouldn't touch because I had just started on this project. But I did know that if there was no diff, I wasn't breaking anything and it was guaranteed to work. So what is it about Pulumi that specifically allows for this approach? This is not something we get for free and not something that applies in every situation. As a point of reference, we can go back to the dark days where a human operator had to manually manage the cloud resources and update an inventory list to track what was deployed. You can replace the cloud with a data center or something else, but really the point I'm trying to make here is that this is a situation where the human is interacting directly with the service provider and any tracking has to be done manually. You can imagine all sorts of reasons you might need this list, such as compliance and billing. Pulumi improves on this situation by automating the generation of the inventory list and automating the sync with the cloud resources. However, the inventory list is still the main interface here. The human operator is still reviewing it. There's still a human in the loop to check what matches should actually be deployed. I think most people are using Pulumi this way. They'll look at the preview and make sure nothing crazy is happening. So it's not the only way. The software that interacts with the cloud provider could have its own internal state. This is more like a Kubernetes operator, and it could automatically reconcile that state and keep it up to date. And deployments would look more like migrations of code over this inventory-based approach. But that's not what we're dealing with this declarative infrastructure. We interact with this inventory list. We see this inventory list. We see the specific resources that are deployed in the cloud provider. And the purpose of the Pulumi code that we are writing is to generate this list of resources. So Pulumi's job is to display that for confirmation and then sync it with the cloud provider. And I know this seems basic, but I want to get this mental model down now because everything about how you interact with these tools is rooted in this. If every time you're writing any Pulumi code, you keep in mind and remember the purpose of this code is to generate a list of resources. The purpose of this code is to generate a list of resources. That will change the way you write Pulumi code. And that can really help you reason about issues, take advantage of the power of Pulumi, but also avoid some of the potential pitfalls, which I'll talk about later. Speaking of where this can hurt you and where you want to keep this programming model in mind, we're on to Act 2, the painful untangling. So this section is about the issues we ran into, the style issues, the structural issues, and how we dealt with them using the zero-diff refactor. So all of these suggestions, you can make these changes without actually changing what resources are deployed. They're just how you write the code to deploy those resources, how you write the code to generate this inventory list. So I'll specifically focus in this section how writing Pulumi code is a bit different from writing other types of software, and what the practical implications are of dealing with this inventory list and sync type of model. So now we have this concept of an inventory list, or a declarative list of all the cloud resources that we intend to deploy. The first thing we can do, if we want to think about how this affects the way we should write Pulumi programs, is map this to a concept that we're already familiar with in software development, so we know how to reason about it. This way we don't have to rethink everything from scratch. We can just reuse techniques we've already learned. So one thing that I think most engineers at this point have realized is that storing a lot of state in a giant global variable is not necessarily the best coding style. You end up with hidden side effects and surprising coupling between different parts of your code. Now, this may seem like a bit of a stretch to compare this to a Pulumi program, but I actually think it's the right mapping because it immediately puts us in a defensive mindset. We know to be wary of global variables. We know to be wary of hidden side effects. And by taking this new concept and mapping it to something we already know to watch out for and be careful about, I think that puts us in the right mindset to write better Pulumi code. So to give just one example, conceptual example, one defense against the issues caused by global state is to pull up the interaction with the global state so that it's very clear where the global state is being modified and how the decisions about how to modify the global state are all in one place and very obvious. So I'll talk about how this actually relates to Pulumi next. Now let's get into some more specific examples about what it means to make it obvious how this list of resources is being modified. This is an example of something that is very tempting and feels right, and actually is right in other contexts, but is actually a huge trap in the Pulumi programming model. So two things we think a lot about in infrastructure automation are idempotency and self-healing. And if we're thinking along those lines, a function that ensures a resource exists and then returns its ID is a great idea. If it's not there, or unhealthy for whatever reason, calling that function will correct the situation and eventually bring everything back to the way it's supposed to be. This is a bad idea when using a declarative tool like Pulumi. Because it's written as if we're writing one type of software, the imperative reactive automation, but we're not in that environment. Pulumi is very good at solving the annoying and challenging problem of resource tracking and inventory management, but at the end of the day, the interaction point with the cloud provider is this final list of resources that we're syncing up to the cloud provider state. We aren't running some sort of tight control loop that's just checking that resource and then reconciling it to the desired state. We're actually generating this list of resources that we're syncing all as a group. So let's take a look here at the first example. We're calling cluster 4 on a specific region. And just like this ensure exists pattern, it will return the ID of an existing cluster if it exists, and if the cluster does not exist, specifically in this case in the inventory list, it will create the cluster, return it back to us. Now, you have to ask the question, if you delete this line of code and then run PulumiUP, will Pulumi delete this cluster? And the answer is, by looking at this, we have no idea what will happen. Because if this function is called with this region anywhere else in the code base, the cluster won't be deleted. But if it's not, the cluster will be deleted. And so we have this sort of non-determinism here where we have to understand the whole project to understand the impact of deleting this one line of code. Now in this second example, it looks like it could be bad style in other contexts. How do we know there's already a cluster for that region? What happens if this cluster isn't there? In Pulumi, this will just fail at preview time. This is very explicit. It'll prompt us to add the cluster creation in the one place that clusters are created. And so it's obvious what would happen if we deleted this line. So that's an example of an anti-pattern in Pulumi, but let's try to be a bit more proactive and think about how we might break down a Pulumi program. So there are really three major function types in Pulumi: resource creation functions, input functions, and configuration functions. And this is specifically if we are trying to break down a Pulumi program and separate things into our own libraries. We should think of it this way, because the way we treat these functions are a bit different. So for example, resource creation functions modify this global inventory list. They modify the list of resources that, when the Pulumi program completes, is what we plan to deploy to the cloud provider. So these functions should deterministically create resources. Any resources that they depend on should be passed in. You should be able to know exactly what will be created when you call the function. So at the top level, it's clear what resource will exist, and it's clear what will be deleted if we remove this line of code. Inputs are pretty simple, but in a way they're also interacting with the global state, so it's worth separating these out. They can include stack inputs and current infrastructure state. There's nothing too complicated there, but they're a different function type. And finally, configuration functions. So these build the inputs to our resources, and they are inherently more dynamic because they don't change what's deployed, but they change how things are deployed. And this is usually what is actually dynamic in infrastructure. This is usually what we want to change. These are things like ECS container IDs or AMIs or number of instances in our autoscaling group. And it can be a bit blurry because, for example, the number of instances in an autoscaling group configuration, even though that doesn't actually change which resources are deployed, might actually spin up new instances behind the scenes. And the line is really, does it change something in the list of resources we are deploying? Because that is ultimately what Pulumi is tracking. So that number in an autoscaling group is really configuration. It's not a resource. So that's really the dynamic part. And finally, I had to mention this because anyone who has dealt with declarative infrastructure tools long enough knows that resource naming can be a huge pain. Because Pulumi is using these to track the resources you have deployed, And the cloud provider also might have limitations on things like name lengths. So these are just some tips on some things to watch out for, but I would spend some time thinking about this and going with what works for you, because every situation is a bit different. One thing that we don't do in our infrastructure that I wish we did a bit more, and I think we're going to move to this, is to explicitly pass in some kind of namespace argument to your resource creation functions. Something that you expect to be unique even if you deploy multiple instances of that resource. So imagine you have a function that's a resource creation function that's deploying multiple resources, and you just want to create an identical parallel copy to that stack. Being able to pass in a namespace argument would allow you to do that without running into these name collisions. Okay, so we talked about all these coding style things, but the actual migration is really the payoff. For us, this was obviously the most stressful part because this was a stage where we actually ended up changing our infrastructure in a way that might affect users. So the way we ended up doing this was we deployed a completely new stack in parallel to our old stack. We set up the same AWS Route 53 traffic policy that we used to route users to the nearest region, to do weighted routing so that we could send a percentage of traffic to the old stack and a percentage of traffic to the new stack, and gradually migrate users over when we were confident that the new stack was working. And the important thing here is that we were sharing code and running everything on the same commit, so the amount of thinking we had to do at this stage was low. In my opinion, that's really ideal. You want the most stressful part to be the part where you can turn your brain off and not have to make critical decisions. So in this section, I'll talk more about how we structured things to be able to do this, which was possible because we followed the patterns that I presented in the last section. So one thing we ended up after doing all this refactoring was very thin projects. The project directory is where you run PulumiUP. And in our monolithic project, we had a lot of business logic that had to be pulled out during the refactor, and they were all in the same project directory. Now our projects have only one index.ts file because we're using TypeScript, and the per stack configuration like production or staging or development. So basically only those files, none of the business logic is actually in the project directory. So for the migration itself, that allowed us to reuse code so we could be clear about what was changing and what was really net new infrastructure. And the things that were shared, we knew that they were working because they were already deployed on the old stack. And the things that were new, we could really focus in on that and make sure that we were getting that right. This also means that in the future, if we want to do a complex migration on something that's shared between two different projects, we just need to change it in the library. And even if it's a multi-stage migration, we can make sure that we're doing it consistently across all our projects. Besides pulling the business logic into libraries, you can also think about how to separate your Pulumi projects. Now, I don't think it's worth separating everything into its own project, but if you have one component that you're frequently updating, that's probably a good candidate. Also, it's probably worth separating the difficult to change parts of your infrastructure into their own projects. So for example, the base VPC is probably difficult to change and will change very rarely. So that might make sense to put in its own project. It would also be imported by a lot of different projects. On the other hand, the DNS records, traffic policies, and load balancers, they might not change frequently because that's not a core part of your application, and they're also a bit riskier to change because they're user-facing. So that also might be worth putting into its own project. I would also recommend putting the export types into libraries so that when one project exports something, they can use the types in the library to export those variables, and then the project that's importing them can use consistent types, so you get some type checking across project boundaries. So what was the result? In the end, we were very happy with how this turned out. We now rotate our container instances in the background on a periodic schedule, but our actual service deployments are orders of magnitude faster. During this migration, as I mentioned earlier, we also found a lot of subtle assumptions that the application was making about having dedicated access to a SQLite database on a dedicated volume. And some of these were kind of scary assumptions that completely broke the model, and we really had to update the application to deal with that. But because of the way we did the migration, we were able to deal with these bit by bit safely in the background and in a way that was completely invisible to our users. So as you can see here, previously even a good deployment would take minutes, but now we measure our deployment in seconds. This changes the way we do development and makes our infrastructure more reliable because we can recover much more quickly from incidents. And now that we have control of the underlying host, it opens up new possibilities for taking control of the storage layer and doing other types of optimizations. All right, so thank you all for watching. I hope this was useful, and feel free to reach out if you have any questions. I love just generally talking through infrastructure problems and thinking of ways to make infrastructure work boring. And it doesn't even have to be related to authorization. Just feel free to reach out. If you do have an authorization question, anyone at OSO would be happy to help. So you can also reach out to the OSO team at this link. All right, thank you for your time, and I hope you have a good rest of your day.